Let's say you want to sell books online. You would probably start with a simple three-tier architecture. Your clients, such as web browsers or mobile applications, would use a REST to interact with your backend application. Over time, as you grow your business, you attract more and more clients and want to start selling different items and add additional features. At some point, you decide to break down your monolith into multiple applications or microservices, which you can develop, deploy, and scale independently. Well, since you've been using a REST from the beginning and are familiar with it, you decide to use a REST as well for service-to-service communications. Let's keep it very simple and say you have user, inventory, catalog, and shopping cart microservices. Let's say a user browses the catalog, adds a book to their cart, and the system checks if it's in stock. For that, your shopping cart calls the inventory service, and the JSON response might look something like that, which would be around 154 bytes. On the other hand, when a user browses a catalog, the system might generate personalized book recommendations based on their past orders or profile. In this case, the catalog service calls the user service, and the JSON response might look like this, around 119 bytes. And finally, when restocking items, the inventory service might need detailed product information, for example supplier details, from the catalog service to update stock accurately. The JSON response would look like this, around 288 bytes. By themselves, those numbers don't mean anything. For simplicity, let's just say that all those interactions form a single request, and you get 100,000 requests per second. That would be around 53.5 megabytes per second, or 132 terabytes per month of network traffic. What if I can tell you that you can significantly reduce this number, as well as reduce latency and potentially increase your throughput? Not to mention that it will make your infrastructure cheaper. Let me explain. When you use a REST API, you send back and forth quite large, human-readable JSON payloads, which are great for public APIs and easy to develop and debug because they are human-readable. But at some point, when you scale, you need to think about efficiency. gRPC, instead of using JSON, uses Protobuf, which is a binary format and significantly smaller in size, and it takes less time to serialize and deserialize it. Now, instead of JSON, let's estimate Protobuf sizes for the same requests. In the end, we get only 150 bytes compared to 561 bytes in JSON, which is 3.5 times larger than Protobuf. This is the primary reason why it's more efficient, but there are other benefits as well, which we'll discuss later. Also, let's say you host your bookshop on AWS and decide that you need a highly available setup so that in case one data center has issues, your infrastructure can still serve clients. Well, you would spread your instances across different availability zones, but AWS has network charges, and you'll pay 2 cents per gigabyte. Again, for simplicity, let's say all your requests are between different availability zones. So, by using a REST and JSON, you would pay around $2,867 per month for transferring 132 terabytes. In the case of gRPC, it would only be 15 megabytes per second and around 39 terabytes per month, which would reduce your bill, and you would only pay $780 per month. These are just rough estimates, but I hope you get the point. The main reason why JSON is much bigger is that JSON uses key value pairs and nested structures to define attributes and their associated data. In this case, the keys alone take up 22 bytes, and the useful data amounts to only 41 bytes. If you need to send the data over the network to a client, every single time you need to not only send the data you want, like name, address, and maybe a phone number, but also the keys for each piece of data. And depending on the JSON, those keys can be a significant part of the overall size. Let's say we want to make it more efficient. Well, the obvious way is to decouple the schema from the data and only send the data over the network to the client. But now, both the client and server need to have that schema in order to encode and decode our messages. So by decoupling the schema from the data, we reduce the payload size but make it a little bit more complicated to work with and debug. Also, by reducing the data size, we reduce the time needed to serialize that data and also reduce the time that it takes to transmit that data to the client. MTU, or maximum transmission unit, is the number of bytes you can send over the network in one shot. So if you can fit more messages in one unit, you increase the throughput and reduce latency as well. Our sample JSON message is 70 bytes, so you can fit around 20 messages in the data packet and send them in a single transaction to the client. On the other hand, the Protobuf serialized message is only 41 bytes, and we can send around 35 messages. The overall size would depend on the data types you use in your message. Protobuf can encode numbers much more efficiently than JSON, and you'll see much bigger differences. Before gRPC, there was RPC, which is Remote Procedure Call. It is a model where you call a function that runs on another machine, but it feels local to the caller. You call a method, pass arguments, and get a result back. The network exists, but it's intentionally hidden so developers can think in terms of functions instead of sockets and packets. gRPC is a modern open-source RPC framework released by Google in 2015. It takes the RPC idea and standardizes how services define methods, exchange data, and communicate efficiently over the network. And there are two main building blocks of gRPC. First, protocol buffers, or Protobuf for short, which is the data format we just covered. And the second is HTTP2, the transport protocol. It maintains a long-lived connection and supports multiplex streams. And you can use an unencrypted version without TLS in your VPC, where you can relax some security constraints. There are 4 communication patterns you can use in gRPC, and the closest to the REST API is unary. The client sends a single request and waits for the server to send back a single response. It is best for standard CRUD operations. For example, give me the user with ID 5. Next is server streaming. In this scenario, the client sends one request, but the server responds with a whole stream of messages. The client keeps reading from the stream until there are no more messages left. It is best for real-time data feeds, like a stock ticker or a live sports score update. We also have client streaming. This is the reverse of server streaming. The client sends a stream of multiple messages and the server waits until it has received everything before sending back a single final response. It is best for uploading large files or sending a batch of data points for the server to process as a whole. And finally, bidirectional streaming. This is the free-for-all mode. Both the client and the server send a stream of messages to each other simultaneously. They don't have to wait for the other side to finish. They can read and write in any order they like. It can be used in chat applications, multiplayer gaming, or complex real-time coordination. To use gRPC, you first need to define a service definition. You describe your API in a proto file by defining services, methods, and messages, request and response shapes. This file is the contract. Both the client and server are built from it. From that contract, gRPC generates client stub code, methods you call like local functions. It also generates server interfaces, methods you implement with your business logic. When a client calls a gRPC method, it goes through the following flow. First, the request is encoded into Protobuf's binary format. Then, the message travels over an existing HTTP2 stream. The server routes it to the correct method, executes your business logic, creates a response, serializes it, and streams it back to the client. Because it uses HTTP2, many calls share one connection and run in parallel. A slow response doesn't block faster ones behind it, which keeps tail latency under control. You should use gRPC if you have a lot of microservices with high call volume. Also, if your application is latency sensitive and you need to keep latency under control, if you have applications written in different languages, it's easy to generate code stubs from a single proto definition. There are some trade-offs as well. Browsers, for example, don't natively support gRPC, so you need some sort of proxy or gateway. It's more difficult to debug because messages are not human-readable. Also, when you change the message format, you need to regenerate all the code. In general, gRPC is excellent for internal microservices, but for public APIs, REST is still the preferred choice, mainly because of the human-readable nature of JSON and how easy it is to integrate. If you're a developer building modern applications and microservices, you might want to learn about JWT tokens and why you'd prefer them compared to traditional sessions.